Good morning. My name is Matthias Fresacher, and today I'm going to tell you about joint work I did together with Luka, Carroll and James East on finding presentations for semigroups of full domain partitions. So let's get into it with a summary of what this talk is going to cover. First up, I'm going to go through some motivation of the two main ingredients of this talk, that is presentations and then diagram monoids. Moving on to their formal definitions, which will allow me to state the results I was able to prove and give an outline of those proofs. So let's get into it, and starting off with some motivation for presentations. For that, I'm going to make use of a Lego analogy. So suppose we have a collection of Lego bricks, and what can I do with these Lego bricks? Well, I can join them together to get new bricks. For example, if I have two red bricks here, I could join them together to get a new larger brown brick, for example. But there are some limitations on what I can do. Specifically, it could be that two combinations of bricks are equal. So for example here, this particular combination of bricks is the same as this combination, which is the same just as our large brown brick that we just created. And it could also be that sadly, my Lego kit is a little bit small and I've run out of bricks. This nicely captures the idea of a presentation, which has got two parts to it. First, the generators, which we can think of as our collection of the Lego bricks that we started off with, the bricks that we build everything from, and the notion of relations, which captures this idea from down here, where potentially different combinations of bricks actually give us the same larger brick in the end. If you're familiar with group presentations, you can very much think that these are completely analogous except for some minor technical details. Why do we care about presentations? Because they offer computational benefits both for humans and especially for computers. An easy example of this is consider we need to do some calculations on a vector space. It's much easier to work on a basis for that vector space than in working with the entire vector space itself. Or likewise, there's a reason why number theorists love their primes instead of just any old integer. So let's move on to diagram monoids, and for these I'm going to motivate them using an example use case. And this is from the area of statistical thermodynamics, where the individual interactions between atoms is modeled by matrices. These matrices are elements of an algebra, specifically a twisted semigroup algebra, where that semigroup is your favorite diagram monoid. This whole construction is typically called a diagram algebra. And this is not the only use case. There are other examples in fields such as biology, representation theory, invariant theory, knot theory, just to name a few. And obviously, importantly for this conference, the diagram monoids also have very strong combinatorial structures and links within themselves. So now let's get into the more formal definitions of our objects. So starting off, for that we're going to need some basic abstract algebra. Specifically, we're going to need to understand a binary operation on a given set, say X. Binary, two inputs leading to one output. Formally speaking, we have a map X cross X to X. Some easy examples that you're familiar with would be the arithmetic operations, or for example, matrix addition and multiplication. But we can also have some more exotic examples, such as function composition, and in a moment I'm going to show you how we can even make Lego bricks be a part of a binary operation. A binary operation may have some properties. For example, it could be associative. So for me, I'm going to write my binary operation as simply a product. And associative means if I multiply three elements together, if I multiply the first two together first, that should be the same as multiplying the last two first. Addition, well, that is an associative operation, but subtraction is not. The left-hand side here is -1, the right-hand side is +1. It could be that there exists an identity element. So this is a special element which I'm going to denote iota, which if I multiply by any other element on the left or the right, I get back my original element. In essence, the identity element doesn't do anything in our binary operation. Multiplication, well, in multiplication, the number 1 is an identity element. If I have an identity element, it could be that some elements have inverses. So if I have an element, and it has an inverse, if I multiply the two together in either order, I get back my identity element. Basically, the inverse undoes our binary operation. If I'm looking at addition, the inverses would be the negative of a given number. It could also be that our binary operation is commutative. And by that we mean if I multiply two things together, the order that I do that in doesn't matter. So addition, that's a commutative operation, but subtraction is not commutative. From this, I can construct some well-known algebraic objects, probably the most famous of which is the group, where we have a binary operation that is associative. It does have an identity element. We do have inverses, but it is not necessarily commutative. A group is a very special instance of a larger object called a semigroup. Semi, half, so it has got less structure. So here we still have associativity, but that's basically it. We don't necessarily have an identity element, we don't necessarily have inverses, and we're not necessarily commutative. Sitting inside between these two, we have the notion of a monoid. So a monoid is one where we do have associativity and we do have an identity element, but we do not have inverses and we're not necessarily commutative. From this, you may have the sense that the monoid nicely sits in between the two, but that's actually the wrong idea. The monoid is much, much closer to the semigroup than it is to the group. Hence why semigroup theorists study monoids. The final notion we're going to need is that of an idempotent, and this is simply an element. If I multiply it by itself, I get back that same element. In multiplication, the number 1 is an idempotent. So now let's formally define what we mean by a presentation. And for that, we're going to take a set of letters, say X. And for this, I'm going to have a running example where that set is 2 Lego bricks, a red 2x2 brick, and a blue 3x2 brick. I then construct what's known as the free semigroup X+, which is basically all of the words over my set of letters X, where concatenation is the operation. So basically this means, in my Lego example, concatenation, I'm just going to join the bricks in one long row. And then if I've done that, so for example here the blue joined with a red, I'm going to think of this as a new standalone brick, for example here a violet 5x2 brick. A different example could be I could have red, blue, red, red. So any combination of my original red and blues is allowed. In some sort of more formal setting, I could look at the free semigroup generated by 2 elements, say an A and a B, and I can represent this using a Cayley graph. So I have a starting point, then I have the word just A, I have the word just B, but over here I could tack on an A or a B, so I could have the word A or the word A, B. Likewise, up here I can add on another letter A or B, so I could get B or BA. And obviously this pattern just keeps on repeating forever and ever in sort of a fractal tree manner. We then have our set of relations R, which is a subset of X, the free semigroup cross the free semigroup. And an example of this would be the relation that AB is related to BA, which we typically take to mean just AB is equal to BA, which if you recall, that's the commutativity condition. So if we now add this relation here, we're going to get a commutative free semigroup generated by 2 elements. So we're still going to have our word AB, but if I now look at the word BA, well that's going to be exactly the same because of our identity here. So I end up with a square here instead of the tree structure that we had before. And obviously this repeats for all of the different levels continuing on forever. In my Lego example, I do also have some relations that we can make a note of. For example, if I have 3 red blocks, that would give me a block of size 6. Well, that's the same as 2 blue blocks, which are also size 6. And in a similar fashion, if I have blue followed by red, well, that's the same as red followed by blue. So in fact, our Lego bricks, they commute. I then need what's known as a congruence, which I'm not actually going to define formally, but basically just think of the role that a normal subgroup plays in a group environment. And the reason I need a congruence is so that when I take a quotient of the free semigroup by this object, I still end up with a semigroup. That's the whole reason why we quotient up by normal subgroups. In semigroup theory, the equivalent notion is that of a congruence. To get a little bit of a better understanding, let's look at the quotient group we would get from our 2 generators quotient out by the congruence generated by these relations. So this would then be a semigroup where basically we end up with all the possible brick sizes. So 2, 3, 4, 5, 6, and so on. But keep in mind that for each of these, it's an equivalence class because we are quotienting out. So let's look at that in a little bit more detail. So how do we get a 2x2 brick? Well, the only way we can get that is by the red 2x2 brick. So there's only one element in this equivalence class. In a similar vein, how do we get a brick of size 3? Well, it's only the blue one that has got a size 3. For the size 4 brick, well, we get that by having 2 red bricks. And this is then where things start to get a little bit more interesting. To get a size 5 brick, well, I have two choices. I could have blue followed by red, or red first and then blue. And obviously this keeps going up, and the equivalence classes, well, they're just going to get bigger and bigger as more combinations could be used to get a particular size. That now allows me to state more formally what I mean by a semigroup presentation. So we have a semigroup presentation if my semigroup is isomorphic to the free semigroup quotient out by this congruence set. If I have that, then I can say we have a semigroup presentation given by the generating set X by, and our relations R rather. I'm also going to need the monoid version of this. So now I'm going to look at the free monoid, which is our free semigroup joined up with the identity element, which in terms of concatenation is basically just no letters, the empty word, or no bricks in our brick example here. So then sort of analogously, if our monoid is isomorphic to the free monoid quotient out by the congruence set, then I have my monoid presentation, which I can say the monoid has a presentation given by the generating set X and our relations R. The final notion we're going to need is the notion of idempotent generated. And this simply means that our generating set X is entirely made up of idempotents. Moving on to our diagram monoids. So first up is the partition monoid, Pn, and I can think of this or define this formally as all of the elements, or the elements are all of the different partitions of the set 1 up to n union with 1 up to n primed. I can picture this pictorially by drawing my set 1 up to n as just a row of vertices. I can copy this in a second row, that's my primed vertices, and then I can draw some edges, so potentially linking the top or just the bottom rows in non-transversal edges, or linking the top and the bottom rows with a transversal edge. The way we can get between these two notions, a block in the partition here has to correspond to a connected component in our graph. And from that we can see if I were to draw this extra red edge in here, well, the connected components of this graph haven't changed, hence we have the same element in our monoid, but obviously the graph has changed, so the graphical representation is not necessarily unique. Just be careful of that. A presentation for this was first found by East in 2011. We're also going to need the notion of a planar partition monoid. And this basically, planar means that no edges are allowed to cross like they do up here. The graph must be planar inside of this box. The partition monoid contains all of the other diagram monoids. So I'm going to list a few of the commonly known diagram monoids. None of them are actually going to be important for this talk, but it's good just to provide some context. And in the brackets are the authors and years where the presentations for each of these monoids was first established. First up is the Brouwer monoid and its planar counterpart, the Templey-Lieb or Jones monoid. And it actually turns out that it is isomorphic in some sense to the planar partition monoid, and hence we get a presentation for the planar partition monoid through the presentation for Templey-Lieb. We also have partial Brouwer and its planar variety, the Motzkin monoid, and the symmetric inverse and its dual, the dual symmetric inverse. So that brings me to the key diagram monoids that we are going to need for this talk. For that we have the full transformation monoid, Tn, which we can basically think of as a map from a set, which is the top row of vertices, to that same set now the bottom row of vertices. So for example, this element here gets mapped to this element here. From this definition, we can see that the symmetric group is going to be a submonoid of our transformation monoid. And we're also going to need the notion of an order-preserving monoid, On, which is actually the planar part of our full transformation monoid. And this makes sense because every time we cross an edge, well, that's precisely when the order is not preserved. We will need a joined semilattice monoid, En, where semilattice is just a particular type of semigroup, a fairly basic one that I'm not going to define. And join, well, join because we can think of the elements here as being equivalence relations on a given set 1 up to n. And obviously we can take the join of equivalence relations. How do I see this as a graphical monoid? Well, I draw my set n, I draw edges such that the connected components of my graph here correspond to the equivalence classes of my equivalence relation. I then just repeat this in the bottom row and I draw all vertical edges, and that is my diagram of this monoid. Next I have an octopus monoid, or at least that's what I'm calling it, Dn, because it doesn't actually have a name, and unfortunately it's a little bit hard to define formally. So instead I'm just going to make use of a picture to explain to you how it works. And basically it is the planar version of En, so it's going to play a very similar role to En. So in En we have these boxes, we have the same boxes here, but we don't have this bottom side. Instead we have nested non-transversal edges and potentially some isolated vertices as well. And the reason I'm calling it the octopus monoid is because to me it just looks like the tentacles are coming down from the top like an octopus does. Unlike En though, it is not a semilattice, it is only a right regular band. That's a weaker condition. And as I sort of alluded to, this is a new monoid, and as such, as part of our work, we developed a presentation for this because we actually needed that in our proof of our larger result. So that brings me now to concatenation in my partition monoid, and this is the multiplication operation of this monoid. So for those of you that are visual-based learners, this is an animation of that procedure in action, and for everybody else, I'm going to make use of this intermediary step to explain to you how we end up at the concatenated diagram. So let's go through the steps of calculating alpha times beta in some detail. First, I position the two diagrams, one directly underneath the other, and then I draw these red vertical in-between edges. I then remove the two inner rows of vertices, and I remove any floating blocks that are created. So a floating block is any collection of edges that are now not connected to the top or the bottom row of vertices. So here in black is an example of a floating block. And to finish up, I basically just tidy up what I have left. So I'm going to squish my rows back to normal size, and I'm going to draw clean edges where they exist. This operation is associative. It does have an identity diagram, specifically just all vertical edges, but it is not necessarily a commutative operation. That brings me now to the full domain partition monoid, which is the main object of study for this project. And it's defined as being all of the diagrams where every vertex in the top row is connected to a vertex in the bottom row. This is the full domain part in the name. From this definition, we can see that the transformation monoid is going to be a submonoid of this monoid, and also that our joint semilattice monoid, En, is going to be a submonoid. In fact, our full domain partition monoid decomposes into these two monoids. And to see that, well, we first look at all of the non-transversal edges in the bottom row. So here we only have one indicated in blue. From that we create the corresponding joint semilattice element, so having that same box here. And then if we look what we have left, so if we just look at the black edges here, they are just a transformation. So that is the appropriate transformation that we need up here, and that is how we construct our decomposition. Recall that the symmetric group is a submonoid of Tn, and hence a submonoid of our full domain partition monoid. And as such, it now makes sense to talk about the singular ideal part of our monoid, which simply removes this symmetric group part. We're also going to be interested in the planar analog of all of these. So we have the planar full domain partition monoid, and this is where, recall, edges are not allowed to cross. We must be planar inside of the box. Here we find that the order-preserving transformations are a submonoid, and also our octopus monoid Dn is a submonoid. In fact, we have a very analogous decomposition like we did up here into On and Dn. That brings me to the results we were able to prove, starting with the singular ideal result. So here we have a generating set X. This is comprised of Eij's, which are symmetric in the indices, where we take the identity element as a starting point, and in the ith and jth component, we just draw a box. We then have some Tij's, where if I is less than j, I still basically have the identity element, but I end up with sort of a triangular shape here. And in the other case where j is less than I, well, my triangle goes in the opposite direction. It sort of is the mirrored version of it. I then have some relations R for distinct I, J, K, and L, specifically some T relations, some E relations, and then some relations that link the two, which brings me to my theorem from this year, which says that the singular part has a semigroup presentation given by the generating set X and our relations R. In fact, I can do one step better than that. This monoid is idempotent generated, which we can see quite easily that all generators are idempotents by these top two relations. In fact, let's have a look at these relations in a little bit more detail. So let's look at Tij squared, writing out our two t's. If I were to compute this, I can see I just end up with a single triangle block, but that is a Tij as we would expect from an idempotent. The relation also says I can swap the indices on the first t, so let's draw that. So I have my triangle block going in the opposite direction, but it still is linked to that vertex. I still get this diagram. The identity holds as you would expect. Alternatively, let's have a look at two different t's. So the triangle bits are going to be just shifted apart slightly. If I were to compute this, we see that the triangles just sort of get superimposed on each other. Allegedly, these commute, so let's draw it in the other direction. We see the shift is off to the left now, but if I compute this, I still end up with the same diagram that yes, these generators do commute. And obviously the same analysis can be performed on all of the other relations. Next up is the full domain partition monoid. This is where we have a generating set Y. This is comprised of SIs. So SI is just a single cross in the ith position. This generates the entire symmetric group, and then I just have a single E and a single T, and the reason I only need one is because I can make use of the whole symmetric group to generate all of the other E's and all of the other T's that you saw on the previous slide. Then I have some relations Q, where for conciseness, I'm going to define a word W to be this combination of S's. So then I have my relations given here, and my result that says that the full domain partition monoid has a monoid presentation given by the generating set Y and our relations Q. Finally, I have the planar result, and this is for a generating set Z, where we have Fi's, so these are our triangle blocks, but only ever one space apart, because otherwise we would have crossings of edges, which is not allowed. We have GI's, which is the mirrored counterparts, and we have HI's, which are just the boxes, but again, only one space apart, because otherwise we would get crossings of edges. We then have some relations O given as follows, and we have our result that says that the planar monoid has a monoid presentation given by the generating set Z and our relations O. Here we can again do a little bit better. This monoid is also idempotent generated, and we can see that if we were to unpack this first relation just here. In terms of a proof of this result, well, it's going to get a little bit technical because we're going to make use of strong action pairs. Let's take a monoid M and look at the subsemigroup SU of M, where S and U are going to become apparent as I progress. So I can talk about a strong action pair if the following is satisfied. So if U is a submonoid of M, and likewise S is a submonoid of M. And I also need two conditions to be satisfied. U of S has to be a subset of SU for any choice of S, and I also need a left type cancellative property to hold. As ingredients, I'm also going to need the presentation for U and for S, so suppose I have both of these already. And then I can apply a theorem by Carson, Linka, East, Gould, and Senab. Well, in fact, a dual version, which goes as follows. Basically, if an assumption holds, which I'm not going to go through, then SU is going to have a monoid presentation given as follows. So my generating set is just going to be the union of the two original generating sets, which is very nice. As you would expect, the original set of relations is going to appear, and then we get two extra ones which kind of just link everything up and make the whole construction work. I can weaken this result slightly if I now let S only be a sub-semigroup. Then obviously I'm only going to need a semigroup presentation for S, but I basically can still get the same theorem to hold if I adjust the assumption. And obviously I only get a semigroup presentation, but it's still going to have the same form. And again, I need to swap out R1 and R2 for different relations. That now allows me to state an outline of the proofs of our results. So we take the action pair En and the singular part of Tn. We apply this particular theorem. That gives us a presentation for the singular part of our monoid. And then we could apply the monoid version of this theorem to give a presentation for the full domain partition monoid. But instead we apply deduction, which sounds simple, but let me assure you that is a non-trivial step to go from here to here using deduction. On the planar side, as I already alluded to, first step is actually to find a presentation for the octopus monoid Dn, because, well, we need a presentation for both of the monoids in our action pair. This is again a non-trivial exercise because our monoid is not a semilattice, but only a right regular band. But once done, we do get an action pair Dn-On, where we can apply this theorem to get our presentation in the planar setting. So hopefully you have learned some interesting maths with the help of Lego.